Hello, everyone. Today we have Olivia Di Matteo from TRIUMF giving us a talk. Thank you, Olivia, very much for joining us. And Olivia will be talking about qRAM.
Thank you so much for the invitation, Maria. We used to share an office, just in case anybody didn't know. Yeah, so I'm going to talk about quantum RAM, which is a fairly contentious subject. It's something I've been working on for about 2 or 3 years now from the standpoint of like circuit optimization and resource estimation, but like it's caused more than one argument online. So hopefully the talk will at least give you an appreciation as to why that's happening. So before I talk about anything quantum though, I want to take a minute to show some appreciation for classical RAM. I think it's something that a lot of people take for granted. I know certainly I do until I'm in a situation where I want to do something and I don't have enough. Classical RAM is used essentially to store the active state of a computation, or if you're working on some data processing, your data is being stored in the RAM as you're working on it. And classical RAM is great. It's cheap. Like you can get 16 gigabytes of RAM for something like $100 Canadian now. It's fast. Query times are on the order of a few nanoseconds. So it's a really amazing piece of technology. And just in the interest of explaining, I guess, the multiple layers of wordplay in the title, the way that a classical RAM is laid out in hardware, this is a simplified version, but essentially it's a two-dimensional grid, and each square in the grid is a memory cell. And in that cell is a capacitor and a transistor. The capacitor can either hold the charge or not hold the charge, which represents the 1 and the 0 that you might be storing in your memory. And then the transistors are used as like control electronics. So the way a readout happens is that things are organized in columns and rows. So columns are the bit lines, hence reading between the bit lines. And then the word lines go across. And so with this setup, you can address individual cells. And you can also, like, you can read, you can write, and you can do that in any order, hence random access. So as quantum computers get more and more developed, of course, you can see there are a lot of parallels with like classical computing paradigms. So we have kind of quantum circuit synthesis and optimizations like the analog of a compiler. We have quantum error correcting codes and classical error correcting codes. So it stands to reason that classical computers need RAM. They also need something called ROM, which is read-only memory. So quantum computers are also going to need a qRAM and a qROM for certain applications. And so this is where the contention occurs. So some, and I want to stress that it's some and not all, some quantum machine learning algorithms or other quantum algorithms require a qRAM in order to like load classical data onto a quantum computer to run the algorithm. Now, the problem with that is that it's actually not really clear if we're going to be able to do that efficiently. And I want to stress too, that's in a fault tolerant setting. Like if a problem is big enough for us to want to bust out our quantum computer to solve it, it's going to be probably a very big problem, in which case we're going to need a lot of qubits, probably some very big circuits. So we're going to need like full fault tolerance. So essentially what this leads to is if you design a quantum algorithm and it shows maybe some sort of quantum speedup, you have to be really careful, because if you're kind of sweeping under the rug the fact that you have to query this qRAM and it's not clear if the qRAM is going to be efficient in the future, it doesn't really matter how efficient your algorithm is. It's not going to be efficient if you can't get the data on the machine in the first place. So in this talk, I'm going to discuss some of the very early proposals for qRAM. By early, I mean like about 10 years ago. It's still a relatively new subject. I'll talk about the distinction between qRAM and qROM. And then I'll talk about some like very recent work that's been done in the last 6 to 8 months. And finally, I'll end with a discussion about a new library some of us are developing for programming qRAMs and Q#. So let's talk about qRAM and what it is at a more fundamental level. Essentially, you need a qRAM in situations where you have a quantum algorithm that requires you to either store or query or both classical or quantum data in superposition specifically. So you'll have some algorithm, applying a unitary, and then maybe it makes a query to the qRAM. So essentially the qRAM is like an oracle. Now what that query actually looks like when you write it down could be one of many different things. Now the first one, probably a lot of you are familiar with from Grover's algorithm. You can think of this operation that's happening in Grover like flipping the marked state as a qRAM query. You want to read data at some address, and how you want to get the data back is like within the phase of that address. Another way to approach this is to read in data in bits in the state of a qubit. And this is used in a number of algorithms, some of which are for state preparation, and another one is the element distinctness. Solving the decision problem requires a qRAM of this form. You have some string of bits that you want to read, and you want to read it like into the qubit state here. And then the last type, and this is the type I won't really discuss, is the idea of having a complex vector and reading that in as like amplitudes of a superposition. And this one is used quite commonly in quantum machine learning applications, because then this would be like a vector of classical data. So the specific type of qRAM query I'm going to focus on is this type where you're reading in the information as bits. You have a superposition of addresses, and then another register of qubits that's there to hold the answer. What the qRAM query does is it loads up the contents of the memory at each address and puts it in that register like next to the same address. So how do we actually implement this type of query?
Sorry, Olivia.
Yeah.
Just while you're on these really basic concepts, in that previous slide, is it critical for it to be a quantum RAM that this can be loaded in as a superposition here, so like an entangled state effectively, or is it okay if you can load it in somehow as I don't know, so rather than having to load it in as entangled with this other bit, if you could load it in some superposition and then do a controlled operation or something to create the entanglement afterwards, is that where the complexity comes in?
So I guess it kind of depends on the application, but for this specific application, the type of query that you want to do is like very specifically from the start, a superposition. And for each address, you want to like get the data that is stored at that address.
Right. So the entanglement is critical in this instance, at least.
Yes. Yes.
Is that,
so like,
but it's not always the case that entanglement is critical as part of this step.
yeah. So like this type of query here, you're just reading things in as amplitudes. So it's like kind of one data vector at a time. But here it's very specifically like multiple addresses in superposition.
Right. Okay. Thanks.
Yeah. Thanks for asking. Please jump in anytime if you have questions. Okay. So we would like to design a qRAM that does this very particular type of query that I've shown here. So the first algorithm that was produced that did this is called bucket brigade qRAM. And the motivation and the model of bucket brigade qRAM is not really our like two-dimensional grid of memory cells, but rather this binary tree where each of the leaves is like a memory cell. So it stores a 0 or a 1. So if you have n-bit addresses, basically you have 2 to the n memory cells at the bottom. So what we want to do is make a query to this device to get the specific memory contents at a given. Say, okay, at each of these nodes, there's like a transistor, and that can route current left or right. So what we do is to each row of the tree, assign one of the address bits to it. Then if that address bit is 1, have all the transistors in that row send current to the right. Whereas if it's 0, you have them send all the current to the left. So if you do that, then you'll see that exactly one path will have the current routed all the way through to the memory cell. And so then you can make your query. So that works, but that's not very efficient. We've really only used 3 of these nodes, but we had to activate all of them when we have things set up in this way. Now it's really nice conceptually, but it's not efficient. Now here's, I guess, a bigger problem is if you wanted to translate that model directly into a qRAM. For example, maybe you want to put qubits at every point that tell you whether or not to go left or right. But to do that, then you would have, these address qubits. And this address qubit would have to couple with all of the qubits in that row, essentially. And so that's going to get really hairy really fast because there's an exponential number of cells in each row. It grows. So that's a very precarious superposition, and error rates are low. Like, you're not going to want to do something like that. Sorry, error rates are high. Fidelities are low. My bad. Okay, so the way around this is the bucket brigade RAM. So this is just a bucket brigade classical RAM, but rather than having just normal transistors at each node, what you do is you find some electronic component that has 3 states. One of the states is just a weight, and then you have states also that will route current left and right, just like in this other fan-out RAM. So in order to make the query, what you do is you feed the address bits to this tree one at a time. So you start at the first bit, you send it into the tree, and it reaches a node that's in the wait state. So what it does is this node kind of absorbs the state of the address bit that comes in. So this node decides to turn on the part of the electronic component that sends current to the right, because this is a 1. The next bit comes in, it's a 0, so it comes in at the top, it sees that it should go right, and then it reaches another node in the wait state. So it's a 0, so it transforms that node to the left state, and now current goes left coming out of here. And so on for as many address bits as you have. And you can see now that we've carved a single path through the tree rather than having to turn on all of the nodes in the tree going left or right. So the way this translates to the quantum situation is essentially just by turning these trits into qtrits. And then all of these operations that happen, like sending in address bits, changing things from wait to right or from wait to left, you design unitary operations that do that. And I'll show you this because it's exciting, but I made a GIF of the process to illustrate what would be happening for a bucket brigade qRAM. So address bits go in one at a time. They follow the path until they reach a node that's in the wait state, and depending on whether they're 1 or 0, they will change that qtrit state to right or left. Now, after the final address bit is sent in, a quantum bus travels down the tree, goes to the memory cell, couples with the memory and copies the value, and then exits the tree, and all of the qtrits get reset to the wait state. I'll let it just play out one more time. So the advantage of the bucket brigade then is, rather than this fan-out RAM where we had to do things to 2 to the n-1, like all of the nodes in the tree essentially, now we only have to do things to n of the nodes. And this you can query in superposition because all of the operations that are supposed to happen are going to be unitary. and the number of operations is polynomial. So when this paper originally came out, they kind of said, that's great, there's a polynomial number of operations, so maybe we can just get away with error rates that scale as inverse polynomial and we'll be fine. Maybe we don't need active error correction on all of the components. And that may be true for very small qRAMs, very small numbers of queries. But in the context of a larger algorithm such as Grover, when you do want to do a large number of queries, it turns out there's a theoretical result that there's essentially no quantum advantage if you have a faulty oracle. And so what people did later is essentially show that if you have an exponential number of queries in your qRAM, you do have to use fault-tolerant error correction to get that error rate to be exponentially small. So you kind of lose this advantage of not having to do error correction. But then the question, of course, becomes, well, how expensive would that actually be then to run that qRAM? And another question too is, how do we actually express this as a quantum circuit? So everything I've showed you is in terms of these trits and just the qubits being routed through a tree interacting with the qtrits. If we have just like a regular quantum computer with a bunch of qubits, we have to somehow be able to translate this bucket brigade scheme to a regular circuit model on qubits. So we're going to do that. And we're going to do that and then actually look at the resource estimates for this type of qRAM. So to do the resource estimates, what I'm interested in looking at is essentially a space-time trade-off. So I define here a cost, and I look at basically the number of logical qubits in that qRAM multiplied by the T depth, because in a fault-tolerant setting, if it's T gates that are expensive to do, we want to minimize the T depth. So for this talk, I'm going to stay just at the logical layer, but in principle, you can also go down another layer to the actual fault-tolerant layer and look at what would happen if you put this into a surface code. And then you can get things like actual query times, and then like the number of qubits that you'll need to actually do all the fault-tolerant stuff, like the magic state distillation. And we did that in our paper, but I'm not going to go into any detail about that because it depends on a lot of assumptions. And the numbers are also a little bit out of date now, I think. But if you're interested, you can go and check that out. So I think now is a time that's good to pause for questions if anybody has any, before I start showing a bunch of circuits. All right, I will carry on then with the circuits. So this is what the bucket brigade process looks like as a quantum circuit on qubits. There's two main components. What's happening here, we call like an address fan out. And essentially this is the analog of what was happening when we sent the address bits in one at a time in order to carve the path to the memory cell that we wanted. This here is doing the actual query or coupling to the memory cell. So this here is the actual memory. So these are a bunch of qubits that are just sitting there in the 0 and 1 states. We want to query those. And so what happens is that the address gets fanned out, and depending on the address, only one of these qubits will get like lit up and turned to 1. And so that one will couple with its associated memory cell through a Toffoli, and it will change the target bit depending on the memory contents. So you can see here that if we have an n-bit address, we have 2 to the n auxiliary qubits here. We have another 2 to the n qubits in the memory. And this is 2 to the n Toffolis in a row. So the scaling of this is bad. Something like 2 to the n by 2 to the n. But this can be improved on using parallelization. So what you could do is all of these Toffolis that happen sequentially, So maybe we add in some extra qubits, change things so that we do all the topolys at the same time, and then perform some sort of parity calculation to actually like do the output rather than doing all the topolys at once. So you can see now that we're no longer going to have a depth that scales exponentially with the number of address bits. This would just be the depth of like one topoly. But you're still going to have 2 to the n qubits, 2 to the n qubits, and now you've brought in another 2 to the n qubits to affect the parallelization. But doing it that way is actually still slightly better if you look at the t depth and if you look at the actual costs. So when I did these resource estimates, I actually brought in a number of extra qubits in order to parallelize the topolys down to t depth 1. That just adds qubits. Overall, if you look at the costs, we have that 2 to the n by 2 to the n for the original one, and then the parallelized one becomes n times 2 to the n, so it's better. But it's still exponential, so this thing is still very, very expensive. Now that's a qRAM. So in a qRAM, similar to like classical RAMs, we have actual data stored in like physical qubits, and those physical qubits are being queried and coupled with the qubits that are actually, doing the qRAM query. So in our original paper, we called this like an explicit memory because it was explicitly stored. We're moving now towards calling it just a qRAM. So the advantage of a qRAM is that you can query with like essentially data that's unknown. Somebody can just give you a register of qubits. You could use it in your queries. You don't have to care at all about the contents. And writing to this qRAM is really easy. You just need to flip individual bits that are stored in that memory. The disadvantage, though, is that essentially that circuit that I showed you is fixed. You can't really do anything to it that might depend on the contents of the memory that might be able to optimize it more. So it doesn't take advantage really of any internal structure that the data might have. So on the other hand, qROM, which we called implicit memory, the data is known. So what happens is a qROM is essentially like a lookup table. And what happens is that when you query it, you're executing a circuit that will, like, depending on the address you put in, give you the right output because you know what the right output's supposed to be, but without a bunch of extra qubits sitting there actually holding the memory contents. Now, what's more difficult about this, though, is that if you want to write to the qROM, essentially you have to remake your circuit and recompile and reoptimize it. But that said, because you know the structure of the memory, there's maybe some like really nice optimization that you could take advantage of because you know the structure and maybe there's some patterns in the data. So this is another good place for questions, if anybody has one. All right, so let's talk about qROMs then. So this is the simplest way conceptually to make a qROM. So let's suppose that we know the contents of our memory. We know that, for example, we have a 3-bit address and that 4 of those elements in that memory have to be 1. So what we can do is design a circuit such that each of the addresses that contains a 1 will control a flip of the target bit. So here, if you give the address 0, 0, 0, this multi-controlled topoly is going to trigger and flip the output bit to 1. So this one here will work for 0, 0, 1, and so on. And if you have multiple data bits, for example, if you're storing more than a 1-bit number, you just have more lines here and you would be doing essentially the same thing. So what's nice about this circuit is that it uses very, very few qubits. So if you don't want to do any sort of parallelization, of these like mixed polarity gates to reduce the T depth, you can get away with using only n+1 qubits. The issue, of course, though, is that it will be slow. So it's going to be sequentially doing all of these mixed polarity gates. And if you have a very large memory, that's going to take a very long time. So we can do a similar thing as we did for the bucket brigade circuits. We can look at the number of qubits. Here again, I've added some extra ones to parallelize the topolys, but that's not necessary. The point is that it's order of n. And then the T depth here, you can see it's going to depend on the amount of things that are in that memory. So when you multiply them together, you get a total cost that looks like this. So keep that in mind. Just like we parallelized the bucket brigade to see an improvement, we can also parallelize these qROMs. So what I've done here is I've taken all of the address bits and I've fanned them out. I've made multiple copies of them so that I can do all of those mixed polarity gates at the same time. And then we just need to do a little bit of extra stuff to get the output. So this is great because everything's going to be like heavily parallelized, so it's going to run fast. But now, of course, the issue, and this is the same as what happened with the bucket brigade circuit when we parallelized it, we blow up the number of qubits by doing this. But if you actually look at the number, you get the same cost. It's just now we've traded space for time. So I want to point out, though, that this is very much a worst case scenario. So I've not done any optimization on these circuits to get these numbers. In reality, if we know the data that we have, we know what the circuit looks like. And that circuit's a Boolean function. And there are a lot of classical tools for optimizing Boolean functions and coming up with something equivalent that maybe is not just doing a sequence of 2 to the q of these mixed polarity gates that use all of the qubits as controlled. It might be something simpler. But then we would have to actually go and do that and get the resource estimates and see what things look like on average. So that's future work. But other things that could be interesting with the qROMs that we didn't really take advantage of here is that there might be structures of data that just lend themselves really well to being optimized. So one that I kind of found while I was doing my thesis is that when you have like some data that's structured as like a Cartesian product. So if you have maybe in your addresses that contain a 1, you always have the first 2 bits like coming from a specific set and the last 2 bits coming from another set. So something like this. What you can actually do in this case is make 2 qROMs, one that handles each half of this Cartesian product, and then do a topoly on them together. So that shrinks like the size of these mixed polarity gates, but then like you're probably never really going to find this structure in practice. And another thing that I looked at was maybe there's some in-between cases that could also be interesting. Rather than doing these mixed polarity multi-controlled gates using all of the qubits, what if we just did the first half and then using that output then affected more of them on the second half of the data? So we looked at circuits like this, and then there's a lot of things that you can do with parallelization, like maybe you parallelize only this part or only this part, or you could parallelize the whole thing. And this actually ended up being the best option. But overall, it still was very expensive. It didn't work particularly well without optimization. So maybe with optimization, it would have been improved. But there was some really interesting other work that came out that did a similar thing and looked for this trade-off that you can make. And theirs worked very, very well. So this is called a select swap circuit. And like loosely what it does is that you can trade off space for time by essentially making multiple copies of the target register and then writing the memory contents to them. And then what happens is a bunch of swaps here will take the specific output that you want and swap it into this target register. Now that wasn't a great explanation of that, but essentially you have now a parameter that you can play with to change the space-time trade-off. And the more copies of this register you make, the smaller these gates get, but then you get more qubits. But what the complexities look like for this is significantly better. So you can actually solve for an optimal like splitting fraction, and it ends up being the root of the amount of data, which in this case would be 2 to the n over 2. And they calculated the t-depths for this as well, so we can compute the cost, and you get something that's just on the order of 2 to the n. So on the order of the amount of data you have, which of course is better than what the original qROM and the parallelized qROM will give you. All right. Does anybody have any questions before I talk about some of the more recent stuff?
Olivia, can you just remind me that to actually find that optimal value, how difficult is that problem?
I have not worked it out myself, but I don't think it was too bad. I can, it's in the paper how they did it actually.
Okay. Okay, I'll check it out. Thanks.
Yeah.
So far you have been thinking about circuits that essentially classical, they are just reversible, right?
Yeah.
Okay. But like, I think there's a like large literature in classical memory design that you can have classical circuits, and have people think about like you just translate these classical designs and make it reversible and what the circuits would look like?
Yeah, well, I guess actually what I would like to do with these circuits is turn them into their classical counterparts and make use of all of the classical tools. Because as you said, there's a lot of stuff out there for classical circuits.
Yeah. Okay.
It's just a matter of, I guess now, finding the tools, learning how to use the tools, and doing it. All right, so the last 6 to 8 months have been quite interesting for qRAM. There's been a number of new papers that have come out that have made some significant improvements over the circuits that I just showed. In particular, there's been some optimizations done on the bucket brigade qRAM that parallelize a lot of the T-gates in a very nice way. Extremely recently, like just last month, I'm going to show some pictures from this, but people have designed a qRAM that can store quantum states and query those quantum states using simultaneous fan-outs. And a lot of this is happening as, I guess, QML or quantum machine learning comes more into the mainstream, because it's an important problem for QML to be able to do this efficiently. But again, we still are really not sure if it could be done efficiently in the fault-tolerant setting. So a lot of the work that's still being done is just on designing these circuits and doing the resource estimation. So earlier this year, a group parallelized the bucket brigade circuits, and they took advantage of a really cool trick that I want to show you because I just learned it recently and it's really cool. All of these bucket brigade circuits, they have these topolys, and these topolys either share controls or share targets. And you can make some really neat simplifications when you have topolys that share a qubit. So one thing they did was they turned all of these topolys first into controlled Z with a CCZ gate. The ordering of the target and control qubits doesn't matter. So you can turn this set of topolys into a set of CCZs that all share a control. So what happens is if you have two adjacent CCZs that share a control, you can decompose it into this lovely circuit identity. The important part of the circuit identity is how the T's are arranged. So you can see that the T depth of this circuit is 4. It's very small. All of the T's are stacked. And this, you only get like more benefit as you add more and more TOEFLs. So this is what the 2-qubit or 2 address qubit bucket brigade circuit looks like when you make that optimization. So now you can see like very clearly that the T depth of this circuit is going to be linear. So the parallel bucket brigade circuit also had a linear T depth, but we had to bring in a whole bunch of extra qubits to do it. Now you can do it just by taking advantage of this trick with the shared qubit TOEFLs. So at the end of the day though, you end up with essentially the same cost, much fewer qubits. However, you still have the 2 to the n in there just by virtue of it being an explicit memory where you have an actual register of qubits with data stored. So that 2 to the n really is not going away. But now it's not 8 times 2 to the n, it's much smaller, and that's great. And I also just want to highlight that they've actually made their implementations of these circuits available, as well as a resource estimation framework. It's based on circ, so if you're interested, I highly recommend taking a look at this. So the other new development that's just last month's very recent is to take advantage of simultaneous fan out. So what this gate is essentially doing a C0 from the top qubit to every other qubit. And so what that looks like is that it would have like linear depth, or maybe you can kind of do a trick where you do it on 1 and then you kind of split things up and then you can get logarithmic depth. But in some hardware platforms, maybe it's possible to do this fan out simultaneously when you have all-to-all interactions available. And I wanted to just highlight a couple examples here that if you are able to do those fan outs simultaneously in hardware, there's a really, really big advantage for qRAM, because like this is a fan out, this is a fan out. These are simultaneous controlled swaps that could be turned into like also fan outs. And same in this circuit here, fan out, fan out. So a lot of the regular circuit depth, not T depth, is kind of contained in these fan outs. So if we could do them in one step, that's a significant improvement. And so that's just what this group did. They specifically were looking at ion traps because you have the global interaction there. And what they did was design a new type of qRAM that takes advantage of simultaneous fan out. And this is what it looks like. So you can see that you have your address qubits here, you have a memory here. And now instead of that fan out of addresses and sequence of TOEFLs, you just have this nice cascade of controlled swaps that are simultaneous. But the coolest thing about this is that it doesn't just store necessarily classical bits in the memory. These are not limited to being just 0 and 1. These can be actual quantum states, like superpositions. And it works because like instead of doing C0s and TOEFLs, you're doing swaps. So you're like swapping stuff around, swapping it then to the output register, and then swapping things back. All right. The last thing I'll talk about is our work on the new library. But are there any questions beforehand? Okay. We'll carry on. So we are designing a qRAM library in Q#. So probably the first question everyone will have is why Q#? For quite a few different reasons. So one is that it's completely open source, even the compiler is open source. But another big reason is that it's hardware agnostic. So we don't really care about what hardware this qRAM is going to be implemented on, but like we want the ability to use them like in algorithms. And so this way we don't really have to worry about it. But it also has some really neat built-in tools. Specifically, it has a built-in resource estimator, which makes it very easy to do resource estimation. So rather than me writing out formulas by hand, I can just ask the resources estimator, like, how many T-gates does this circuit have? So it's very convenient. It also has tools for like fast Boolean circuit simulation, which means that we can simulate these qROMs very quickly. And there's a couple other things that I'll highlight in the slides. So if you're interested to look, we're doing all of this development openly. So you can go to the Q# community GitHub and find the qRAM library. And you could contribute to it if you like. You can let us know if you find any bugs. And another thing that we're doing though with this development is like we're developing it very openly. We're documenting the development process. And Sarah is actually like one of my collaborators. Probably some of you actually know her. Streams development every week on Twitch. So she sets up like a stream, it's programming. A bunch of us are in like the chat box next to her, and people from all over the world just come to like watch her program and chat about quantum stuff. And so that's been really, really fun. It's a very unique experience. I'd never seen anybody stream coding before. So here are just a few examples of what the library looks like now. It's very much still under development, but our goal is to just try and make it very easy for somebody who's working on a quantum algorithm to like bring in a qRAM and query it with like kind of minimal overhead. So really just treat it as the black box. So far we've designed oracles for the bucket brigade circuits and some qROMs. So this is what our bucket brigade oracle looks like. And the key point is that when you create one of these things, you have access to the normal things that you would usually like to do with a qRAM, such as making a query in this bit form, or making a query in the phase form like you would do for Grover, or writing to the qRAM. So those all become available to the user. And another reason why we use Q#, and this I think is just really cool, is so all of these circuits, especially the bucket brigade ones, they have this fan out of the address, a sequence of toffolies to actually do the query. But then if you want your circuit to be reversible, you have to undo that fan out. So Q# has this framework called like within apply. So you can ask it like, you know, within, which it does some stuff, then it will apply what's in here, and then it will run everything that is in the within backwards. Like it will calculate the adjoint for you and run it backwards. So it reduces the this frequency of programming mistakes that would come when you try and then take a circuit and undo it and do it backwards. So this is what a qROM would look like. It looks a little sparser, I guess, than a qRAM, just because all you can really do with a qROM is read. But the hope is to get this to a point where it's very easy for a user to just like create a memory and be like, read at this address, and they can very easily incorporate it into existing algorithms. And so in addition to doing the development, we're actually trying out some applications as we go along. So I mentioned earlier that Grover's algorithm, you have this reflection about the marked elements in the set, and that that operation can be considered as a qROM query, or qRAM query, sorry. What happens is you have a memory where it's storing 0 in every memory cell except for the marked element. And then when you want to do the reflection about that element, you can do different color here. You can just ask the memory to query the phase rather than programming like the oracle circuit in full. So this is, again, very much a work in progress. This is very preliminary. We're working right now, though, on the resource estimation in particular and documentation. But eventually, we're going to program all of these really cool new qROMs and qRAMs that have come out recently, like in particular, like this select swap one. And I think this new fan out one would be really cool. And finally, I want to integrate it into more applications. So for example, I'm looking into programming just this element distinctness algorithm and incorporating the qRAM into that. And I think that's going to be really neat. So in summary, I guess qRAM is expensive. It's unlikely that we're going to have a full-scale efficient one anytime soon, especially, of course, a full-scale efficient fault-tolerant one. But what we need, of course, are better circuits. And we need to look more closely into different qubit time trade-offs. I think there's a lot of interesting stuff that could be done there. We've already talked a bit about this, but I want to get more realistic resource estimates. Like I can count how many T gates are going to be involved in a qROM where we do all of these mixed polarity gates sequentially. But if we heavily optimize that, how many T gates are there really? And how many T gates would there be for a typical application? So in addition to that, of course, we have to develop tools to do that. And the library, I think, is really going to help us with that. So yeah, thank you for inviting me and for your attention. And I thank all my collaborators, as well as the Unitary Fund, who's funding the development of the library. And especially Sarah, you should come to her stream and watch her program. Thank you.
Okay, thank you, Olivia, very much. This was an excellent, very clear talk. Do we have more questions?
I
see a lot of chat messages. Oh, no.
I'm very curious about this live streaming of the development. I guess there's obviously like a social aspect to it, which is nice, especially in this time. But have you noticed like any? Yeah, can you say a little bit more about like, especially like as an observer, have you found that is helpful, or like does it add anything like really new that is surprising to the development of something like this?
Yeah, so I guess what I found like the most interesting is like I've never really watched someone else program before, and like everybody programs differently, so it's really interesting to see like a different perspective on like how you kind of organize your thinking about making the program. But it's also been very helpful for like debugging, because on more than one occasion I said I made this thing but there's a bug, and then during the stream Sarah will like do tests and like try and find my bug. So that's been very fun. And there's been a surprising amount of just, I'm not sure where people are from, but no, at least some are from like overseas that are tuning in at very odd hours to like watch this happen and contribute to the conversation in the comments.
And I think also maybe just to follow up on that, I get the impression from like the local Australian community that because we're like in a different time zone and we don't have this sort of same kind of buzz around like technology coming from Silicon Valley, that they're just not aware generally of how the field of quantum computing has shifted from like a purely academic pursuit to now what seems like a more kind of developer community focused kind of area. I'm not sure if there's a question there, but maybe if you could comment on that.
No, it's been interesting, but I think it's also been a really good thing because like I can program, but I can't program at like the level of a professional software developer. So the fact that things are becoming like more developers are getting interested in it is very fantastic. They'll do a much better job than I can of making things efficient and user-friendly, I think.
Thanks.
Maybe I can ask a little bit. You mentioned this unitary fund at the end. Can you tell us a bit about how that works? I just was Googling it. It looks like quite an interesting little program. And there aren't that many grants yet. You seem to have one of the not so many grants. So maybe I thought you could tell us a bit about how that works and how it's influenced this.
So it's essentially, I guess, I think they call it like a micro grant. It's like a gift that's meant to fund the development of the project. And so we sent them a proposal, like this is the library that we want to build. This is what we're going to use the money for. And then like they agreed to give us the money. And so at some point, like we meet with them and like, you know, this is what we made and we can showcase it. That's
okay. So it's just a very flexible program for a small amount of money.
yeah, like the range of projects that have been done, like it's very diverse. Like if you look at the list, so like this is a qRAM library in Q#, but people have done things in other languages. They've like made up their whole own frameworks. It's really neat, and they're things that I don't know, maybe would have still gotten done otherwise, but certainly like having the grant and both the money and the motivation is very helpful for getting it done.
Okay, interesting. I might ping you some questions later if I look into it more.
Yeah, by all means.
Thanks.
Can you hear me?
Hi, Sarah.
Hey, I just wanted to maybe add, yes, I'm here. I'm the one who's making chat ping continuously. I wanted to just add on a little bit to your answer to Chris about who's actually watching this. Only about half of the viewers for most of my streams are from the US. The other half are pretty much everywhere around the world, including like Mexico, Turkey, Ireland. Like it's really pretty an interesting mix, and yeah, a lot of times people are up pretty late. So it is a really fun community. You should come hang out and program with us.
There's also a button you can press that makes her give treats to her dog during the stream. It's the best part.
Yeah, Chewy likes that part a lot.
Does that end up being a very, very spoiled dog?
You would think so, but he's a German Shepherd with the attitude of like an 80-year-old man. So the offer of free food is generally met with a, oh, I have to get up again to come get it. So he's fine.
Special guest on the stream quite often.
So I have maybe a question that I think might be useful to some of our students or new students that are kind of coming into, like through the university system, interested in quantum computing, that might think, oh, I really want to get involved in like these open source projects, but like I don't know where to start. Like, do you have any advice for those students? Like, where can they start? Because I think for many, it might seem a bit intimidating to think that they have to make a pull request and go through quite a rigorous process. But maybe it's not so. Doesn't have to be that way if you know the right entry point.
Yeah, I don't know if I'm the best person to answer that because I am still kind of always hesitant to like go and make a pull request on someone else's thing. But I guess like good starting points are like finding bugs, clarifying things in the docs, because sometimes the docs aren't good, but then like as you learn and start to figure things out, maybe you can make a contribution to making that process better. And it's not as daunting, I guess, as like working on the actual code and making a pull request, but it's like still making a contribution.
Right. So like you like starting with the documentation and I know of some of these open source projects I've looked at have very weak documentation. So that's probably a good starting point you suggest?
I think so.
Yeah, okay.
Do you know of any good resources for people to be able to just learn a little bit about that overall coding process, the collaborative coding process in that sort of environment?
I don't really know of any specific resources. Like, I guess I've learned through experience and from asking colleagues, and also like reading the Git documentation, which is surprisingly good. But in terms of anything concrete, I don't really have any suggestions.
Right.
If you
Okay.
don't mind me
I mean,
hopping in.
yeah, I guess
Sorry.
I was asking more about the social like almost the social aspect, where like not in terms of the, but in terms of the kind of the actual interaction. How does this, not the technical details of how Git works, but how does the process work in a, like, following from Chris's question?
Yeah, I guess I'm a bit introverted and afraid to talk to people, but understanding that, like, I don't know, if a random person comes and talks to me, like, I'd be more than happy to tell them about my stuff. So most people are the same, and it's just kind of have to do it, I guess. But Sarah, you wanted to add something, I think.
I was just going to, I'm providing links to support here. But I think, so a lot of repos follow the, like, tag issues and stuff as good first issues. So I know like a lot of the Q# repos have this, and that's basically like places or issues or bugs that people have identified that are a good place to start. A lot of projects also will have kind of like mentorship sort of. So I put a link here in chat to opensourcediversity.org, which actually has a couple really neat guides that I just found recently for like what it's like to go through and make your first PR or make your first contributions. And there's good resources both for like students as well as people who are maintaining projects and want to kind of facilitate that that interaction and help people kind of onboard. Other good resources, I think, are like finding if there's a community around a particular language or something like that. You know, hop on their Slack, Discord, whatever, and just ask somebody to help. I think that's usually you know, having kind of a co-pilot on some of that stuff can be really helpful.
Great. Yeah, that's very interesting. I mean, we, I guess, have, like, as a scientific coder, I grew up just making all of my own stuff, I guess, like many of us here. And like, I'm aware of the fact that there's this whole other world of, you know, collaborative code development. And now that I am sort of building my own group, we have a bunch of projects and we're trying to do this in the right way. But not having the experience myself, I'm not a very good, it's a bit hard for me to kind of guide that process. And but it's a really interesting one. I think from what I can see, it's something that would be really valuable for a lot of these things that people work on.
Yeah, I wish I had the opportunity to do something like this while I was in school. Like, this is the first project that's actually been like a real collaborative development project. Like, everything else I've just kind of done on my own. So it's a very different experience. But also,
Right.
you learn so much more.
Yeah. Well, it's really good to have some good examples of that. So thanks very much.
If I may.
Yeah.
One thing that I'd like to mention is, you know, like, I mean, we, like Chris Ferry and I, and along with several others, you know, we had a lot of fun with making qInfer back in the day as a collaborative research project in software, and also as a software project, both. And I think one of the things I really learned from that, and have been learning again with all of the open source work I've done outside of that, has been it's okay to make mistakes. You know, if you make them in good faith and you have the right approach to kind of recover from that. It's not like people expect, you know, you do this step, this step, this step, and it has to absolutely be perfect. you know, we're all humans, we're collaborating, and, you know, I mean, I think it like, just as it's okay to, you know, make mistakes and like kind of research notes as you're collaborating with others and you fix them and you find them. That's a really important part of the collaborative process, is helping each other improve and work through that. So I think it doesn't have to be like this fear that if you don't do things perfectly from step one, it's terrible. Why are we doing this? But
yeah, I think it's for me, it's not so much that like I've made too many mistakes to feel too much embarrassment about making mistakes, or at least I wouldn't have got this far if I did. But I guess it's more the fact that like there's this, you know, these things where you face there's kind of an invisible steep learning curve to just like to just get in the door kind of thing. There's this I just don't quite know the language. It's almost like a translation issue, not knowing the right language, not quite having the right tools on your desk. You know that if you want to sit down and do coding, you need a computer and you need some sort of software to develop in. But you know, there's all these other tools for these open source projects that you kind of it somehow feels like there's an invisible barrier to getting in, and it's that and I know, I think Chris, I know you have a blog post from a number of years ago now about, I think, open science development or something, which was really interesting, and that was one of the things that got me first interested in this concept. But nevertheless, I haven't quite managed to get over the threshold yet somehow.
I definitely have like the latent fear still that I am going to just like totally nerf our GitHub repo. It hasn't happened yet, but
There's always ref
might.
log. There's literally nothing you can do to get rid of it. Unless you are maliciously trying to remove things. You're safe.
Yeah, I've come close with a couple of grant applications, doing something in a rush at the last minute where came close to almost completely deleting an important branch in the code, but fortunately not yet.
I guess I told my student, like, at some point you will probably break something in the GitHub repo, and when you do, just let me know and we will fix it. And like, I guess that's the experience I had when people were teaching me Git, and I thought that was very helpful. Thank you,
Yes,
Chris.
I think the experience many people have when learning Git is breaking things.
Okay, thank you very much for the talk and the wonderful discussion. Make sure to check out all the links about Q# and libraries and quantum computing development. We will make sure to have them on YouTube, and you can also find some of them in the advertisement for Olivia's talk. And yeah, if you want to chat later, you know where to find Olivia and Sarah and Chris. So thank you very much, Olivia.
Thank you.